Okay, this is a few notes on projectile motion. Now, projectiles are actually nothing new. They don't use any new physics that you've not met. It's a combination of Suvat equations, so the equations of constant acceleration, and a little bit about vectors, and believe it or not, the speed, distance, time equation. And all it does is it combines those three things together. So it's nothing new, it's just a new way of using them. Okay, so a projectile, first of all, is any object that's kind of thrown. Once it's been thrown, it has no other forces acting on it other than gravity. We do ignore air resistance in all of these problems because they do massively complicate the maths, and we want to learn the basics first. So aeroplanes and things like that are not projectiles. Fireworks and missiles are not projectiles. They both have thrust, aeroplanes have lift. So we are just looking at things that are thrown. So they're giving an initial force, and then once they are released, they become a projectile. And that's the bit which we're interested in. The problem with projectile problems from maths point of view is you've now got 2 dimensions. So you've got horizontal motion and you've got vertical motion. And a little bit like where we took vectors that went at odd angles and split them up into horizontal and vertical motion, and then deal with each direction separately, we do the same thing with projectiles. Okay, horizontally, what you're generally looking at is the velocity component. So rather than forces in this case, we're looking at the velocities. Now, horizontally, provided we ignore air resistance, the horizontal component of velocity is constant. And the simple reason is that there's no force acting on it horizontally to change its velocity. So horizontally, it's just essentially a speed, distance, time problem. It's a constant speed, there's no acceleration. Okay, gravity acts vertically. There's nothing to affect the horizontal motion at all. Vertically, so this is the up and down motion. In this direction, we've got gravity acting, okay? So in equal amounts of time, it doesn't cover equal displacements or equal distances. In the case of this cannon, what you can see that the cannonball has been fired out. Initially, it's been fired horizontally, which is the easiest set of problems we'll start looking at. So horizontally, this forward arrow, the horizontal component of velocity, is always the same. Okay? Downwards, the horizontal velocity increases, so it gets faster and faster and it covers greater distances the more time goes on. There's no air resistance, so there's no effect of terminal velocity or anything here. The theory we're looking at is where something just gets faster and faster and faster as it falls, vertically. But horizontally, totally remains constant. So what we have to do is combine the 2 components together. When you put the forward sort of uniform motion and the downwards accelerated motion together, we get the path, which is what we refer to as the trajectory. And because it's accelerating, it's parabolic in nature. So if it was to be an equation, it would be, like an x squared sort of equation. So it's creating that kind of shape. Okay, so starting to look at projectiles that are launched horizontally, so a little bit like the cannon we just looked at. So we mean like this. Okay, so projectiles which are fired forwards. For all types of projectiles, we need to use 2 equations, but in this case, things get a little bit easier. Horizontally, we are just using essentially speed, distance, time. Now, the thing to keep track of is that when we're talking about displacements, we're talking about horizontal displacements. So literally how far something has moved that way, okay? And when we're talking about ux, we're talking about the initial velocity, which is constant, but in the x direction. So this isn't the velocity that something is fired with necessarily, but when it's launched horizontally, that is the case. Vertically, we need a different equation. Because vertically there's acceleration, we need to use the equations of constant motion. So we need the Suvat equations. And the one we tend to use is the S equals ut equals half at squared. Now remember, a couple of things. Firstly, S is displacement, but this is the vertical displacement, so in the y direction, the up and down. U is the initial velocity, but it's in the y direction, so it's the up and down initial velocity. Uy and ux are different numbers. They may be linked, that's something we will get to a little bit later on. Acceleration, of course, is downwards. So very often it helps with these sorts of problems just to take down as being positive. And the acceleration would therefore be g, 9.81. Unless you're doing projectiles problems on Mars or something, in which case take a different number. The only thing that links these two equations together, if you remember thinking back to the Suvat problems, you had u, v, a and s were all vectors. T was the only scalar. So the thing that's constant across these two is the t. The time it travels vertically for and the time it travels horizontally for will be the same. Now, in the case of horizontally launched projectiles, this uy term is 0. Have a look at y. When something's fired forwards horizontally, if you just look at the forwards motion, that's constant. If you look at the downwards motion, it's the same as a ball that's just been dropped. So a ball that's dropped, its initial velocity is u. And that can simplify this equation quite a lot because that term disappears. So although it's still a quadratic equation, it just simplifies to s equals a half at squared or a half gt squared, which means it's a lot easier to solve. It gets a little bit more complicated later on when we look at projectiles that are fired at an angle. Okay, so just a quick example. I don't like doing too many examples in these things, but just to show you what we're talking about now, things are getting a bit more complicated. So you've got an aeroplane, it's travelling horizontally 100 metres per second, and it's 500 metres high. The pilot drops some supplies. Now what this really means is the aeroplane's sort of irrelevant. The supplies are released, and at this point, they're going forwards at the same speed the aeroplane was. So when they're released here, they're going forwards at 100 metres a second. Okay, but vertically, they've been dropped. So to solve a problem like this, what we're going to do is we're going to look at the horizontal motion and the vertical motion completely separate. So one of the questions we can answer is how long is the drop in the air? So in other words, how long does it take to hit the floor? And how far would it actually travel? Now, if this was a cannonball, you could say how long would it take to hit the ground, and what would the range of it be? That's the same question. All right, so just to look at your U, V, A, S, and T, or Suvat if you prefer. I don't know why I just like doing U, V, A, S, and T. U is 0. So this is working vertically. Now, sometimes it really helps actually to write, just before you start doing your workings, write the word vertically. I know it seems stupid, but in your head, it makes you think about things vertically. So we're really not interested in any other direction. So the start speed is 0. It is not 100. 100 is the horizontal start velocity. We don't want that. We're working vertically. We ignore the 100. The 100 has no effect on this whatsoever. Vertically, the start speed is 0 because it's just been dropped. We're only interested in the vertical motion. V is the speed it'll have when it hits the floor, so we don't know what that is yet. A is the acceleration, which is 9.81 metres per second squared. Could be negative, but we can choose whether to make down negative. As most of our vectors are going to be pointing down, it might make sense to make down positive instead. S is the height. Again, this is the vertical distance that it falls. So vertical, not horizontal. And T is the time, of course, it's going to take to hit the floor. So if we take UVAST or SUVAT working just on those vertical numbers, we're actually using S equals UT plus a half AT squared. U is 0, so that simplifies down to just S equals a half AT squared. And it gives us an answer of 10.1 seconds. To do part B, how far away from the point it's released will it actually land? Remember, the vertical motion doesn't have acceleration. So the big mistake people make here is not in getting the UVAST bit wrong, but they then try and apply uvast horizontally. You can't do it, there's no acceleration. A is 0. Okay? You just need speed, distance and time. The distance it travels, the horizontal distance, is the horizontal speed multiplied by the time it's in the air for. Or if you prefer, the horizontal displacement is the horizontal velocity multiplied by the time it's in the air for. So we've already got 10.1 seconds multiplied by the horizontal speed, and we know the horizontal speed was 100 meters per second. So that's where that comes in. If you've used the 100 before now, you've done it wrong. Put all that together, of course, gives us 1,010 meters. So this will be launched at 100 meters per second that way. When it hits the ground, it will be going 100 meters per second forwards, but it will also have a downwards component of its velocity. And horizontally, it will have travelled just over 1,000 meters before, bump, it hits the floor. Okay, so that's a slightly easier projectiles problem. Slightly more complicated projectile problems are where a projectile is launched at an angle to the ground. So with the cannon problem, you wouldn't fire it directly forwards, it wouldn't go very far. You'd actually angle it up in the air. Now this is slightly more complicated, but it still uses the same ideas. Horizontally, the motion and the direction is still constant. So you're just looking at horizontal motion, that velocity is constant. And again, vertically, there's acceleration. The difference is now that it starts by being thrown up in the air. So it gets higher and higher and higher, slows down, stops, and falls back down again. Exactly the same as if you'd taken a ball and just thrown it up. So you've got that up and down motion combined with a forward motion, which means essentially it does that, and it does that. So put all those things together, you again get a parabolic shape. It's just this time you've got the full parabola, whereas on the previous one you only got sort of half of it. Okay, so very often what you get given then is an actual start velocity. So maybe an angle, a projectile gets launched at a certain angle at a certain speed. So the angle is theta, and it's being launched at a velocity of u. Now, in your calculation, you are not going to use this value of u. What you're going to do is you're going to work out the two components, horizontal and vertical. They're the only numbers you're going to use. So the first thing you do in any projectiles problem is you get rid of that and you never use it again. You want u sine theta and u cos theta. Now remember that little shortcut we talked about in the vectors notes. We want u, I want this component of u, to get to that component it's through the angle, which makes it u cos theta. If you want the component that's the opposite way, it's sine theta. Cos theta is through the angle, sine theta is the other way. Little shortcut saves you having to think about trig because you've got a lot of other things to think about right now. Okay, so if we just consider the vertical component first, and we'll look at the vertical motion. Right, so a few things we can do. We can work out what maximum height it will reach. So this thing is going to have a trajectory, something like that. So what we want to know is how high up in the air it's going to go. So we do a uvast for it, u, v, s, and t. We don't know the time yet, but we do know at maximum height, vertically, its speed is going to be 0. So its vertical velocity is going to be 0 at the highest point. Now, I know that it's still moving forwards, but remember we're working vertically, so we ignore the horizontal motion completely. It has no effect at all. The only thing that links the two together, remember, is the time. So vertically, the end velocity is v and 0. So the initial vertical velocity is this u sine theta term. That was the speed it was fired up at in the first place. So u is u sine theta. G, well in this case it probably makes sense to have downwards as being negative because we've got upwards motion as well. So we'll take g as minus 9.81. And then we can use the equations of motion to get s. So v squared equals u squared plus 2as. In this case we've put a g in, so the negative's gone in there as well. You don't have to do that, you can just put minus 9.81 in when you put your numbers in. Rearrange it, nice and easy. So you can work out the vertical height. Now, Once you've got the height, you can work out the time it's in the air. There's a couple of ways of doing this. You can either work out how long it'll take to get to its highest point, so again, just a vertical UVAS problem, or you can work out how long it'll take to go up and down again. And the little trick to that is if something goes up and then comes down, this end speed will be the same as the start speed was, but it'll be negative, it'll be in the opposite direction. And if you put all those numbers in, either it'll cancel out to zero, in which case you use a different equation, or you'll get the answer of the time. If you just find the time for the highest point, you don't need to do another UVAS calculation to get the full time in the air. You can just double it. So if you've got the time to the highest point, double that gives you the time it's in the air, provided it's returning to the same height. If this was being fired at an angle off a cliff and it was going to land a lot lower, then you have to take a slightly more complicated approach. Okay. That's it for this, just a bit of a talk through. Obviously there'll be some examples in the class, and there is a Word document with this, which does have a little bit more detail on if you want to go through it, but hopefully that just covers some of the basics. You get your hands on some of the examples, it starts making a little bit more sense. So it looks very complicated, but actually it's just a series of processes you already now know how to do, and it's just keeping track of your numbers. And this really is important that you lay out your workings very carefully. So things like when you're working vertically or horizontally, saying so in your notes. I mean, as much as it's good practice to say exactly what you're doing anyway, it helps you to keep track of your own workings. So it's always a good idea to be clear when you're working horizontally and vertically, and that way you don't end up putting the wrong numbers in the wrong places. And of course, a diagram at the top of the question, so you can see which numbers are horizontal and vertical velocities, is an absolute must. So prepare your information and the questions become a lot easier to answer.